Okay, so in this video we're going to be looking at how optical isomerism can be used to determine which mechanism is predominating, whether it's SN1 or SN2. In order to do that, we need to look at the formula of the species that is being attacked by the nucleophile. So in the SN1 mechanism, it's the carbocation intermediate that is being attacked, and I'm just going to use R groups to stand for any carbon chain, but that's the carbocation intermediate that's being attacked. In the SN2 mechanism, it's the starting halogenoalkane that's being attacked, and again I'm just using bromoalkane as an example with an R group here indicating that it's a primary halogenoalkane. Okay, so we're going to look at the attacking species in each of the mechanisms. So in an SN1 mechanism, we have our planar carbocation. So I'm going to try and draw it planar. Okay, not the easiest thing, but anyway. So I've got my R groups here, and this is planar. In other words, it's flat. Okay, and that means that the OH group can attack the bottom of the molecule, so it can attack underneath, or it can attack from the top. So it's got two ways that it can attack. It can attack from the bottom, or it can attack from the top, because the carbocation structure is a planar structure. If we look at the SN2 mechanism, the OH group can only attack from one direction. So if we look at the transition state for an SN2 mechanism, we've got the two hydrogens, which I'm just going to keep out of the way there, and my R group, which I'm going to keep out of the way there. Then we've got the halogen leaving on one side, and we've got the OH group attacking from the opposite side. So the OH group can only attack this carbon from the opposite side to the leaving group. So there's got to be a bond angle here between the incoming OH group and the outgoing Br group of 180. So first one, SN1, you've got 50% of them attacking from the top, 50% of them attacking from the bottom. In the second one, in SN2 mechanism, you've got the OH group attacking the carbon from the opposite side to the leaving group. Now we need to think about how that could impact on the optical isomerism. So if you think about something like 2-chlorobutane, it's a secondary halogenoalkane, so I'm not overly sure whether it's going to be an SN1 or an SN2 mechanism. Now if I take an optically pure sample of 2-chlorobutane, in other words it only has one enantiomer, and I react it with sodium hydroxide, if the resulting product shows no optical activity, I can use that to tell me whether or not the reaction is going to be SN1 or SN2. So let's have a think about the 2-chlorobutane. So here's my butane molecule. My chloro is on that second carbon. It's an optically active molecule because it has non-superimposable mirror images. I can tell that because it contains a chiral carbon here. Now, for this molecule, it would convert, when it's reacted with the sodium hydroxide, into this molecule. So I'm going to replace the Cl with an OH group. So potentially, it still is an optically active compound. It still has a chiral carbon, it still has non-superimposable images. So how could it show no optical activity? So this is going back to something we looked at in our isomerism pack. We said that if we had two enantiomers of equal amounts of the different versions of the optical isomer, one would rotate it by a certain amount in one direction, the other would rotate it by the same amount in the opposite direction. So if we had both versions of this optical isomer, half would rotate one way and half would rotate the other way. So overall, we would get no optical activity. And that's what's going on in this case. Now that means that the mechanism must be SN1. Why must it be SN1? Well, it goes back to the shape of the carbocation again and the OH group attacking. So, the carbocation is planar. Remember? Therefore, the OH group can attack from two different sides, probably better to say opposite. You get equal amounts of both enantiomers. Therefore, you form what we call a racemic mixture. Because the carbocation is planar, remember that means that this OH group can attack from the top or the bottom from opposite sides of the molecule. You therefore get equal amounts of both of the enantiomers, and therefore you get a racemic mixture. If, on the other hand, I do the same experiment and I end up with an optically pure product, well, it would have to be SN2. And if you remember, it's back again to the shape of the species that's being attacked by the nucleophile. So that's my transition state, that thing in the box. So here, if you remember, there is only one direction that that OH group can attack that carbon, this dotted line, and that is the opposite side to the leaving group. So this group is going out as this group is going in, but you can't attack this carbon from any direction. It can only be attacked from the opposite side to the leaving group. So, the transition state, which is what we're talking about here, the OH group can only attack from the opposite side to the leaving group. So there's only one direction that this OH group can attack, and it can only attack from the opposite to this leaving BR group. Therefore, three dots, only one optical isomer, one enantiomer. Enantiomer can be formed. So we can have a look at the optical activity of the product. If the optical activity of the product is active, in other words, if it can rotate the plane of plane polarized light, and we've started with an optically pure sample, then we will know that we have an SN2 mechanism. If there's no effect on the plane of plane polarized light and we've started with an optically pure sample at the beginning, we will know we've got an SN1 mechanism. Okay, so the second mechanism we're looking at is the one we looked at in the carbonyls notes, and this is the nucleophilic addition reaction of aldehydes and ketones with HCN in the presence of KCN. So again, we're thinking about how optical isomerism can help us in this mechanism. So we're going to look at the mechanism between ethanal and HCN. So it's hydrogen cyanide again in the presence of potassium cyanide. So I'm going to start with my ethanal molecule here. And again, we need to be very careful about the shape of what's being attacked. So in this case, I'm attacking this carbonyl group here. And this carbonyl group is planar. So again, my cyanide group can come in from the bottom, or it can come in from the top, here. Either way, we get our intermediate, where my cyanide group, I'm just going to draw it down the bottom, has come in, and we've got our O negative there. So that's my intermediate, and then I take a new molecule of HCN, lone pair on the oxygen, attacks that hydrogen, pushing the electrons onto the CN part of the molecule, and we get our product. We've extended the carbon chain by 1 because we've now got this cyanide group added on, and I've got my OH. Now you should notice that this here gives me a chiral compound. So I've got a chiral carbon, so I've got my 4 groups, and therefore I can form non-superimposable mirror images. So there are 2 enantiomers of this one. But we go back to this step here. Remember, I said that this was planar, and therefore there is an equal opportunity for the CN group to attack from the top or the bottom. So we end up with a racemic mixture. And it's a similar argument to the argument as why we end up with a racemic mixture when we do an SN1 mechanism, because the species being attacked is planar. We just need to be very careful that we determine which species is being attacked. So because the carbonyl group, and be careful here you don't say the molecule or you don't say anything else, it's the carbonyl group is planar. Therefore, the cyanide group, nucleophile, can attack from opposite sides as it did in the SN1 mechanism. Therefore, you get a racemic mix and basically equal amounts of both optical isomers, in other words both enantiomers, so therefore optical rotation cancels out. So because we've got that planar shape on this carbonyl group, notice the molecule overall is not planar, but I'm only interested in this site that's being attacked. So the carbonyl group is planar, therefore the cyanide group can attack from top or bottom. You get a 50-50 mix, so you get equal amounts of both enantiomers being formed, and therefore although you have here the chiral carbon with the 4 groups around it, overall this is not optically active because you've got equal amounts of both enantiomers. So if we now look at propanone with hydrogen cyanide in the presence of potassium cyanide, we have a very similar starting point. Again, I have my carbonyl group and it's planar around that carbonyl group. My cyanides can attack, pushing the pi-bonded electrons out, and we get our intermediate with our CN group on it and our O negative because I've popped the pi-bonded electrons out. And then we're going to squeeze this along the top, and then we've got this group here pulling off a hydrogen from the CN group, pushing the electrons onto there. So we get our final product with our CN attached, and now we've got an OH group. And in this case, there is no chiral carbon. This carbon with the CN group is not chiral because you've got 2 groups which are the same, 2 CH3 groups. So the answer here is a symmetrical molecule with no optical isomers. Why? Again, carbonyl group is planar, and CN can attack from opposite sides, but product is or has no chiral carbon, therefore its mirror images are superimposable. So no, therefore no optical isomers. Doesn't matter which way that CN group attacks this carbon from, over here, or at the top of the molecule or the bottom of the molecule, you're not going to end up with a chiral carbon here, so you're going to end up with a symmetrical molecule with no optical isomers because I've got no chiral carbon here. Okay, so that finishes the notes on optical isomerism. So that pack is due in on Friday with all the questions at the back answered. There's also a Wednesday checkup. We'd like you to do the quiz on Godalming Online. So do remember that you can contact us through Teams or through email if you've got any questions or you get stuck on anything and want me to go over any other bits. But till then, take care, stay safe, bye bye.